Welcome to The Explainer. Today we're diving into something really cool, the peaks and valleys of functions. What if I told you there's a mathematical tool that can find the absolute top of any hill and the very bottom of any dip? Well, that's exactly what we're going to do. We're finding maximums and minimums using derivatives.
Kinda sounds like a riddle, doesn't it? What on earth could connect a business trying to squeeze out every last dollar of profit with that stomach-dropping lurch you feel at the bottom of a roller coaster? I mean, on the surface, they're from totally different worlds, but in the language of math, they share a pretty fascinating secret.
And that secret, well, it's actually super simple. Both the highest possible peak and the lowest possible valley happen at a place we can call a flat spot. It's a single point where, just for a brief moment, everything levels out.
All right, so our first mission is what I'm calling the hunt for the zero slope. We're going to figure out what this whole flat spot idea really means in math, and more importantly, how we can actually find it.
And the main tool we're going to use for this hunt is the derivative. The easiest way to think about it is like a high-tech slope detector. You give it a curve, and the derivative can tell you the exact steepness, the slope, at any single point you want to look at.
And this right here, this is the absolute key to everything. Think about it. When you're at the very, very top of a hill or the bottom of a valley, those are our turning points. You're not going up anymore and you're not going down yet. For just one split second, the path is perfectly flat, and a flat slope is a slope of zero. That's our target.
So with all that in mind, what's our real mission here? If we need to find the highest point or the lowest point of any function, what is the one single thing we need to be looking for?
And that leads us right into our step-by-step guide. Let's stop talking theory and actually put this into practice. We're going to see how this idea turns into a simple but really powerful three-step method. Okay, here we go. Let's take the function f of x equals x squared minus 6x. Step 1, we find the derivative, which turns out to be 2x minus 6. Step 2, we take that derivative and we set it equal to our magic number, 0. And finally, step 3, we just solve that simple equation, and we get x equals 3. That's it. It's that simple. We've just found the exact location of our flat spot.
Okay, that's awesome. We found the location of the flat spot is at x equals 3. But, and this is a big but, we still have a crucial question. Is this the top of a hill, a maximum, or is it the bottom of a valley, a minimum? How do we know?
Well, for these kinds of functions, called parabolas, there's a really cool and simple visual shortcut. All you have to do is look at the term with the x squared. If it's positive, like in our first example, the curve opens up, kind of like a smile. That means our point has to be a minimum. If that term is negative, the curve opens down, like a frown, which tells us our point is a maximum. Simple as that.
Okay, so the theory is one thing, right? But the real magic happens when we can actually use this stuff. Let's take this method out of the textbook and use it to solve a genuine, real-world problem.
So let's picture this. A farmer has a specific amount of fencing, exactly 30 meters of it, and they want to build a rectangular pen for their animals.
Now, this farmer wants to be efficient. They want to get the most possible space, the biggest area, for their animals using only that 30 meters of fence. So the question is a classic optimization problem. What is the absolute largest area the farmer can possibly enclose? We're hunting for a maximum. And look at this! We're using the exact same steps we just learned. First, you have to get the area into a function of one side, x. Then you find its derivative. Next, you set that derivative to 0 and solve, which tells us one side of the pen should be 7.5 meters. And that gives us our answer, a maximum possible area of 56.25 square meters. Same method, totally concrete answer.
So far, we've really focused on the how of all this, which is fantastic. But to really, truly master a concept and make it stick, you've got to understand the why. Why does this whole process actually work?
Let's just tackle that big question head on. Why? Why is setting the derivative to 0 the magic key that unlocks these special points every single time?
See, it's not some random math rule we just have to memorize. It's pure logic. The derivative is the slope, right? And maximums and minimums are just turning points. And at the exact instant that a curve turns, it has to be momentarily flat before it can change direction. So when we set the derivative to 0, all we're really doing is telling the math, hey, go find me that flat spot.
And for the final piece of the puzzle, let's just lock this down. We found the spot, we know why we found it, but how can we be absolutely sure if we're standing on top of a mountain or at the bottom of a canyon? Well, we have two really great methods. The first one we've already used. For those parabolas, just check the sign. A positive sign gives you a smile, which means a minimum. A negative sign gives you a frown, which is a maximum. And for trickier curves, there's another powerful tool called the second derivative test. Now, you don't need to stress about the details, but it basically looks at how the slope itself is changing to tell if the curve is shaped like a bowl holding water, that's a minimum, or a hill shedding water, that's a maximum.
So what you have now isn't just a math trick. It's a tool used by engineers to design stronger bridges, by economists to find maximum profit, by scientists everywhere to find the best possible solution. The only question left is for you. From minimizing your costs to maximizing your results, what real-world peak problem will you solve next?